Assalamu alaikum wa rahmatullahi wa barakatuh. This is the third video in our chapter, Work and Energy. At the end of this chapter, you're going to be able to define the average and the instantaneous power. Keep in your mind the ideas that we have taken till now, the definition of the work done by a constant force, the expression of the work done by a constant force, and knowing that the work done is independent of the path followed, the work done by weight is expressed as mg into h initial minus h final. Let's define power. Consider a 10 kilogram box needed to be moved to the 10th floor. There are two options, either with a laborer who will take it upstairs, or it can be put in an elevator and lifted up to just reach the goal. Although the work done on both cases is the same, there is something different about the tasks, the thing that makes using elevator better. It is the time interval during which the work is done. The time taken via elevator is less than that taken by the laborer. From a practical viewpoint, it is interesting to know not only the work done, but also the rate at which it is done. Because of this, we defined the power. Power is the time rate of doing work. Power is also defined as the time rate of energy transfer. We're going to define the average power and the instantaneous power. The average power. If an external force is applied to an object which we assume acts as a particle, and if the work done by this force in the time interval delta t is W, then the average power expended during this interval is defined as the amount of energy transferred or work done divided by the time delta t, written as P average equals to the work over delta t. The work done on the object contributes to a variation in the energy of the object. Therefore, a more general definition of power is the time rate of energy transfer. Now, according to the units, we can see that the power equals to work over delta t means work is in joules, delta t is in seconds, then the power is in watt, where watt equals to joule per second. Let's consider this example. The question is, calculate the average power of a motor consuming 1/70,000th joules to produce mechanical energy during 2.4 minutes. Here we can apply the rule P average equals to work over delta T. Work here is given as 1/70,000th, where delta T is given in minutes. We should find it in seconds, then 2.4 times 60. Now we can calculate it and find it in watt. We still have the instantaneous power. In a manner similar to how we approached the definition of velocity and acceleration, we can define the instantaneous power as the limiting value of the average power as t approaches 0. Then we can write it as P instantaneous equals to the limit of work over delta t as delta t goes to 0. Then it is the derivative of work versus time, where we have represented the small amount of change of work done by dw. We can write dw equals to F vector dot product with dr vector, where dr vector represents the displacement. The power then is written as F vector dot dr vector by dt. We know from the last chapter that dr vector by dt equals the instantaneous velocity. Then the power can be written as F vector dot v instantaneous vector, which is finally represented as F times v instantaneous times cosine the angle between F and v. Let's solve this application. A car of mass m moves on a rectilinear and horizontal road with a constant velocity v equals to 72 kilometers per hour. The motor exerts a constant power P equals to 12 kilowatt. The question is, determine the traction force of the motor. Notice here that the power is given, and so is the instantaneous velocity. So we can write P instantaneous equals to F vector dot product with V instantaneous vector, which is F times V instantaneous times cosine the angle. The motor exerts a motive force. Then F and V are parallel with the same direction and the angle is 0. Then P equals to F times V constant. F equals to the power over this speed. Finally, F equals to 12 times 10 exponent to 3 watt over 72 divided by 3.6 meters per second. What for we divided 72 by 3.6? If the unit of the power is watt, it means that F in SI unit in newtons and the speed in meters per second. So we should divide the speed by 3.6 in order to make it in meters per second. This is the end of this chapter. Please keep in your mind that the power is the amount of energy transfer per unit time, and we have average power equals to the watt over delta T, while the instantaneous power is F, V instantaneous, cosine the angle between them. Study well, and thank you for watching.